So this is a recording of the last problem session for the course. And in these problem sessions, we have been doing two things. Review some calculus of one variable material, and then do the problems from the material of multivariable calculus that has been recently covered. So we'll start with the calculus of one variable review, where we have two differentiations and two integrations, and I think we left some interesting problems for the end of the course. So the first is to take the derivative of 2 to the 3 to the x. Here, the way I like to think about this is to designate an inner function. In this case, the inner function will be 3 to the x. Think of it as 2 to the y. Think of 2 to the 3 to the x as 2 to the y, and ask the question what the derivative of 2 to the y is, and the answer is 2 to the y ln 2. I will not write y explicitly, so I will just write it as 3 to the x times ln 2, and then the chain rule dictates that we should multiply by the derivative of what we designated as y, which is the derivative of 3 to the x, and the derivative of 3 to the x is 3 to the x times ln 3. So these are the two parts of the chain rule. And I hope that this method of applying the chain rule will become apparent in the next example, where we have a double application of the chain rule. So here I will begin by designating as my inner function to be sine of cosine x. So in the big picture, I'm looking at cosine of y, and the derivative of cosine of y is negative sine of y. Again, I never write y, I just write what was designated as y, meaning sine of cosine x. And then I'm supposed to multiply by the derivative of what we designated as y. I'm not doing it directly as I did in the previous example, because this needs one more application of the chain rule. So I'm carrying with me my sine of cosine x that I found in the previous step, and now it's a fresh problem. What is the derivative of sine of cosine x? So we designate cosine x as y. We're looking at sine of y, and the derivative of sine of y is cosine of y. Again, we never write y, we write cosine x, and we multiply by the derivative of the inner function of what was designated as y, which is the derivative of cosine x, which is negative sine x. And that's our derivative. Then we have two integration problems that are going to be very, very interesting. So the first integration problem is one that involves a partial fraction decomposition. It's the method of partial fractions, as we call it, and that pretty much entails a factorization of the denominator. The denominator through the remark that -1 is a root of the denominator, and by using synthetic division, we can see that it's written this way, and this polynomial right here has no roots. So this dictates a partial fraction decomposition that looks like this. So 1 over x cubed plus 1 should be a over x plus 1 plus bx plus c over x squared minus x plus 1. And we clear denominators. Some people don't even write this as a fraction. They just go directly to the comparison of the numerators. But here, basically what we're saying is that the number 1 should be equal to this quantity. Why? Because the denominators, you have two fractions that are equal and the denominators are equal. Hence, the numerator should be equal. And now this implies what? We can easily find a by plugging in x equals -1. Why? Because this makes the second term 0. and we will get 1 is equal to a times what? You will get 1 plus 1 plus 1, so a times 3. So that means that a is equal to 1/3. Now, if we expand this quantity right here, then we'll get an a plus b times x squared. And as for x, we will get a minus a plus b plus c times x. And the constant is not really needed, but let's write it for the sake of completeness, which is a plus c. Actually, we might use it, a plus c. So, so by the fact that a plus b should be equal to 0, why should it be equal to 0? Because this has no x squared in it, it's just a constant. We get that b is equal to -1/3. And now we could work with the coefficient of x, but I think it's simpler to work with the coefficient of, with the constant. So a plus c should be equal to the number 1, which means that c should be equal to 1 minus 1/3, which is 2/3. And we got our 3 coefficients, which means that our integral breaks into what? It breaks into the integral of 1/3 of x plus of 1 over x plus 1. And we can factor out in 1/3 from the second one, so we will have 1/3 times minus x plus 2 over x squared minus x plus 1 dx. We should do these two integrals separately. So the integral of the first one is easily found by using a substitution u is equal to x plus 1. And it's ln of absolute value of x plus 1 plus c. The second one is a much more interesting one. So we need to begin by completing the square at the bottom. So this gives us x squared minus 2 times 1/2 x plus 1/2 squared minus 1/2 squared. This is a standard method for completing the square. There are more, but these 3 things together give us x minus 1/2 squared, and then we have plus 3/4. And now the idea is that we need to actually create this x minus 1/2 square so as to break the integral into 2 parts. One where we will do a substitution, and another where the base of the integration will be the arctangent. So how do I create the x minus 1/2? I take the x and I subtract 1/2, and I also add 1/2 plus 2 over x minus 1/2 plus 3/4 dx, and this is equal to what? So I will have the integral of x minus 1/2 over x minus 1/2 squared plus 3/4 dx. So I broke this part off, if you like. And then the remaining one is 2 minus 1/2, which is 3/2. And this will be, so plus 3/2 times the integral of dx over x minus 1/2 squared plus 3/4. I claim that these integrals can be computed now directly. For this one, we will use the substitution u is equal to x minus 1/2 squared plus 3/4, and du will be 2 times x minus 1/2 dx. That's the upshot, that what you get on the top is 1/2 du. So this will be negative 1/2 the integral of du over u, pretty much, which will give you negative 1/2 of ln of absolute value. The absolute value is irrelevant here because this is always positive, and if you multiply back in the whole thing, you will get what we had in the beginning. So that's the first part. For the second part, you can do a substitution. U is equal to x minus 1/2, and pretty much use the fact that in general, the integral of du over u squared plus a squared is equal to 1 over a arctan of u over a plus c. So this particular integral will be 3/2 times, so a here is, a square is 3/4, which means that a is square root of 3 over 2. So this will be 2 over square root of 3 times arctangent of 2 over square root of 3 x minus 1/2 plus c. So you get a couple of things to cancel here. And 3 over square root of 3 is square root of 3. And let's see if we can put everything together. So we will have, let's see, so finally our integral, so the final answer will be, so we had that 1/3 ln of x plus 1. And then we had what? We had another 1/3 that we took out. And the antiderivative that we found here was negative 1/2 ln of, we said the absolute value is not needed, x squared minus x plus 1 plus square root of 3 times arctangent of 2 over square root of 3 times x minus 1/2 plus c. Okay, certainly a very inclusive integral, one that has all sorts of things in it. And the second integral is an improper integral, which means that we have to express it by using a certain limit. One could see that the integral converges using a comparison test, but this will be the integral from 2 to b of dx over x squared minus 1. This has a simple partial fraction decomposition, much simpler than the previous one, which, to speed things up a little, let me just say that this is 1/2 times 1 over x minus 1 minus 1/2 1 over x plus 1. And so this will become the limit as b tends to infinity. What is an antiderivative now for this function? You can find it by doing two substitutions. So this will be 1/2 ln of absolute value of x minus 1 minus 1/2 ln of absolute value of x plus 1. And you want to go from 2 to b. And what are you going to get this way? You're going to get the limit as b tends to infinity. Let's write this as 1/2 ln, apply the properties of the logarithm. So this will become b minus 1 over b plus 1. Remember that the difference of two logarithms is the logarithm of the quotient. And if you plug in 2, you will get 1/2 ln of 1 minus 1/2 ln of 3. So this will be the limit as b tends to infinity of 1/2 ln of absolute value of b minus 1 over b plus 1 minus, actually ln of 1 is 0, and minus minus will give you plus 1/2 of ln of 3. Now, as b tends to infinity, this quantity in here tends to 1, which means that this whole thing will tend to ln of 1, which is 0. So the only thing that survives the limit is this 1/2 ln of 3, which is the final answer for this integral. Okay, with this review completed, let's turn to the main plate for the day, which is the 3 problems that have to do with vector surface integrals, the Green-Stokes formula, and the divergence theorem. And I think it makes sense before we continue with these problems to actually recall the theory behind these 3 items. So we start with the definition of the vector surface, or the computational formula for the vector surface integral. We have a surface S, which is oriented by the choice of a normal vector. And we have a vector field defined all around this surface. The truth is that we just need to have it defined on the surface itself, and we would like to compute the vector surface integral, which can be written either this way, which is the way that I like, or the way that the book has it, which is this way. Either way, it's a flux integral. And basically, in order to compute it, you need to start with a parameterization for your surface patch over some domain T. And this is G of uv, called this parameterization. And that parameterization will give rise to a normal vector, which has to be chosen so that it's compatible with the orientation. This really means that you find a normal vector and you figure out whether it's compatible. If it is, that's great. If it's not, you multiply it by -1. That's all that it means. And eventually what happens is that this will be the double integral over the domain of the parameterization of the composite of the vector field with the parameterization. I like to call this the pullback of the vector field onto the domain of the parameterization, dotted with a normal vector, and integrated over the domain of the parameterization. So that's the definition for the computation formula for a vector surface integral. Now, let's recall the Green-Stokes formula. So the Green-Stokes formula tells us that if we have a surface patch, so let's think of it as S, and let's say that it has a boundary which is oriented in a certain way, and the surface patch is oriented in a way compatible to the boundary. That compatibility really means that if you stand on the boundary facing the way of the orientation of the boundary, and you stand in the way dictated by the normal vector, then the domain is on your left hand. In this particular picture that I drew here has such a pair of compatible orientations. Then what we can say is that the vector line integral on the boundary, which very traditionally is denoted like this, the partial of S, it's really the boundary of f dr, is equal to the vector surface integral over S of f dn. I'm sorry, of the curl of f this formula is very similar to it's a non-planar version of Green's theorem. So this is the curl of f dn, or as your book might prefer, curl of f dot n ds. Here I should say that the curl is formally defined as the partial, the gradient operator cross f, which really means that if f is PQR, then this is I, j, k, partial with respect to x, partial with respect to y, partial with respect to z, and then PQR, which will give you, of course, delete the first row and the first column. That will give you r sub y minus q sub z. For the middle coordinate, don't forget to put a negative sign. What do you put inside? Delete the first row, delete the second column, and you will have r sub x minus p sub z. And finally, for the last, you get pretty much what you have in Green's theorem, which is q sub x minus p sub y. And that's it. Okay, so this is the Green-Stokes formula. And the last result is what we have in the case of a closed surface, one that doesn't have a boundary. It's oriented with the outward normal. So we're talking about the outer flux of a vector field F through that surface. And it turns out that this is equal to the triple integral of the divergence of F in the interior. So here, S is actually the boundary of U. Now, what is the divergence? The divergence, again, can be defined in a formal way as the gradient operator dot with a vector field, which is pretty much if your vector field is PQR, this would be P sub x plus Q sub y plus R sub z. So this is a theoretical reminder of what these problems that we're going to see are about. And let's get started with these problems. So the first problem is a computation of a vector surface integral. So we have the vector surface integral of vector field x square minus y, x plus z. Again, the notation here should have been NDS. And the surface S is described as a part of the plane x plus y plus z is equal to 3. It's exactly the part that lies above the square 0, 1 cross 0, 1. Here, the standard parameterization is the graph parameterization. You think about it this way, that this can be solved for z, representing this as the graph of the function 3 minus x minus y. How do you get a graph? You juxtapose the input with the output. The input here is u and v, the output is 3 minus u minus v, and the domain of this parameterization is going to be 0, 1 cross 0, 1. What you will need here is the normal vector. Normal vector is simply g sub u cross g sub v. What do we mean by g sub u cross g sub v? We take the partial derivatives in all the coordinates of g with respect to u first, then with respect to v, and we take their cross product. So this will be 1, 0, negative 1 cross 0, 1, negative 1, which will be I, j, k, 1, 0, negative 1, 0, 1, negative 1. If you do this cross product, you will get 1, 1, 1. In the problem, this surface is oriented by taking the upward normal. We have to ask if the normal vector that we just found is compatible with that orientation, and it is because the last coordinate is positive. So what do we do next? The underlying vector field is x squared minus y x plus z. This means that if we compose this with a parameterization, we will put wherever we have an x u, wherever we have y v, wherever we have z, we will put 3 minus u minus v. And that will give us u squared minus v and u plus 3 minus u minus v. So this cancels with that and gives us the slightly simpler u squared minus v and 3 minus v. And basically what we need to do is take the dot product of this pullback of the vector field onto the domain of the parameterization with a normal vector. So this will be u squared minus v 3 minus v dot 1 1 1, which will give us u squared minus v, I'm sorry, plus 3 minus v. And we need to take the integral of this. Fortunately, we're integrating on 0, 1. This should be very, very straightforward integrations, giving us 1/3 minus 1/2 plus 3 minus 1/2. This is 1/3 plus 2, which is 7/3. And that's the computation of this integral. Again, it should be very useful for you to pause the video and try to redo this yourselves. And let's go to the next one, which is the computation of the application of the Green-Stokes formula to this integral, vector line integral, z plus y squared dx plus 2x minus z dy plus x squared minus y dz. And here the domain is defined as a triangle defined by the points 1, 0, 0. Then you have 0, 1, 0, and you have 0, 0, 2, which you can ask what plane this is. It's x plus y plus z over 2 is equal to 1. How do I know this? There is a general formula, the formula of the intercepts. If you have a plane that intersects the three axes at points other than the origin, so you have 0, P0, and let's say here 0, 0, C, then the equation of this plane is given by x over a plus y over b plus z over c is equal to 1. So you don't need to do any of the things that we learned at the beginning of the course, finding normal vectors and so on. And the reason why this equation works is simply because all 3 points fit into that equation, they satisfy it, and also it's the equation of a plane, so it has to be the correct equation. Here I should go back and add that our triangle is oriented this way. This is given by the problem, which means that the corresponding compatible orientation for the interior of the triangle is like this. It's the upward orientation. So let's write down the parameterization and actually compute the corresponding normal vector that will both be needed, since by applying the Green-Stokes formula, we will get a vector surface integral. So let's begin with this stage right here. So g of uv is going to be u comma v comma 2 minus 2u minus 2v. How in the world did I get 2 minus 2u minus 2v? Simply by solving for z here. If you solve for z, you will have 2 minus 2x minus 2y. So we can think of this triangle as a graph of this particular function. On which domain? On this domain. Let's describe this domain. Let's call it D. This is all u's and v's such that u is between 0 and 1 minus v, and v is between 0 and 1. Simply because this domain intersects, is a triangle formed by this line that intersects both axes at 1. So 1, 0 here, if you like, 0, 1 here, and this is what we have. Now, the normal vector, since we're at it, let's compute the normal vector. The normal vector is going to be G sub u cross G sub v, which is 1, 0, negative 2 cross 0, 1, negative 2, which is I, j, k, 1, 0, negative 2, 0, 1, negative 2. So this will give us 2, 2, and 1. And we can see that the last coordinate is positive, which means that it's compatible with our orientation. And yeah, what is the next thing that we need to use? Well, don't forget that where's our formula? Remember that we said that we need to take the curl of the underlying vector field and take the vector surface integral. That's what the Green-Stokes formula dictates. And what is the curl of this vector field? So the curl of this vector field is going to be I, j, k, and put the differentiations on the second row, and the components of the vector field in the third row. And what are we going to find? So for the first coordinate, take the derivative of, let me just show it. You need to multiply this with that, which means take the derivative with respect to y of x squared minus y and subtract from it the derivative with respect to z of 2x minus z. So this will be what? It will be minus 1 minus negative 1. This will give you 0 in other words. And for the middle coordinate, get ready to put everything in a parenthesis with a negative sign because it's a middle coordinate. Delete first row, delete second column, and you will have 2x minus 1. And the last one will be 2 minus 2y. So the whole thing is going to be 0, 1 minus 2x, and 2 minus 2y. Okay, so I think we have everything that we need. So let's consider now the pullback of the curl, I'm sorry, of f on the domain of the parameterization. Simply put, we just need to compose the curl with the parameterization. This means that wherever you see an X, you will put U. Wherever you see a Y, you will put V. Wherever you see a Z, you will put 2 minus 2U minus 2V. And this will give us what? It will give us 0, 1 minus 2U, 2 minus 2V. Finally, we need to take the dot product of this curl with the normal vector. And this will be the dot product of 0, 1 minus 2U, 2 minus 2V dot 2, 2, 1, which will give us 2 minus 4U plus 2 minus 2V, which is 4 minus 4U minus 2V. And we need to integrate this. So let's do it on a new board too. So we need to take the integral over the domain that we call D of 4 minus 4U minus 2V dA. How does this work? So we have the integral from 0 to 1 minus U dV, 0 to 1 du, and we have 4 minus 4U minus 2V. Let's take the antiderivative of the quantity with respect to V, so that will give us 4V minus 4UV minus V squared. And this will have to go from actually, I think we had it the other way now. So it was 1 minus V. Yeah. So I'm sorry, allow me to change the order here, because that's how I gave the domain. So we put du first and then dv. Okay, so let's do my integration with respect to u. So I will have what? I will have 4u minus 2u squared minus 2uv, and that will be from 0 to 1 minus v, and dv, which will give us 0 to 1, 4 times 1 minus v, minus 2 times 1 minus v squared, minus 2, 1 minus v times v, dv. Let's try to simplify this as much as we can. So this will be 4 minus 4v minus 2 minus 4v plus 4v actually, minus 2v squared minus 2 plus 2v squared dv. We have a few cancellations here. This cancels with that. And we have, I'm sorry, this goes to v here. So 0 to 1 of 2 minus 2v dv, which is 2 minus 1, which is 1. And that's our final answer. So as you can see, problems like this can be labor intensive because there are many, many things that have to be done. And finally, let's come to our last problem, where we need to compute the outward flux of the vector field F of x, y, z is equal to x cubed y squared plus z, z minus x, through the boundary of the box 0, 1. So find the outward flux of F through the boundary of 0, 1, cross 0, 1, cross 0, 1. By the divergence theorem, this will be the triple integral of the divergence of f over that domain, this dv over the domain u. This is u. And what is the divergence? You have to take the derivative of x cubed with respect to x, that's 3x squared. You have to take the derivative of y squared plus z with respect to y, that's 2y. And you have to take the derivative of z minus x with respect to z, which is 1. And this will be written as an iterated integral. I think this is a very, very simple integration. If you integrate separately 3x squared, separately 2y, separately 1, each of these integrals will give you 1, each of these triple integrals, and the final answer is 3. And this completes the last problem, and these are the problems on the last worksheet, and I think that this completes the problem sessions for our course. Thanks for watching.